Hello everyone, welcome to our presentation for 2021 MENACOM conference. We are three people, me, Hoang, Dirk, Slock, and Jean-Pierre Rossi. Today we are going to present you about our work. It is about 3D self-positioning algorithm based on joint DDoA-ToA. Now let's start. Our presentation has 5 sections. In the first section, we show you the problem formulation. Thanks to the recent developments in antenna design, the direction estimation of a signal is more and more precise, which encourages the directions-based localization. In 3D schemes, the direction of a signal is expressed by 2 elements, azimuth angle and an elevation angle. They are estimated by an antenna array. It can be the uniform circular array or uniform planar array. In any case, we can also estimate the azimuth angle phi I and the elevation angle theta I. In localization, we have 2 positioning approaches in the following figures. The figures is shown in true Cartesian coordinate system. The 2 approaches are the network positioning and self-positioning. In network positioning, the mobile device transmits the signals to all the base stations around, and the position location is estimated at the network of base station. In self-positioning, the mobile device receives the signals from the base stations around, and then it estimate its position by itself. In network positioning, it is straightforward to estimate the phi I and the theta I, because the orientation of the antenna array at the base stations are fixed and unchanged. However, in self-positioning, we do not know the orientation of the mobile device, and this orientation can change at any time. So it is complex to do localization based on the signal, the direction of the signal. And in self-positioning, we have we can only estimate the value phi I and theta I in the reference frame attached to the mobile device. We have phi I is the true azimuth and theta I is the true elevation. Therefore, the estimated azimuth equal to the true value plus estimation error, the azimuth estimation error, and k value of ki multiplied by 2p, where the azimuth estimation error is assumed to be 0 mean Gaussian distributed, and the value of ki is 1, -1, or 0, depending on the sum of phi I and the azimuth estimation error. The estimated elevation equal to the true elevation plus the elevation estimation error, where this error is assumed to be 0 mean Gaussian distributed too. And we can see that when the orientation of the mobile device changes, the value of theta I and phi I change too. Therefore, it is not possible to do the localization based on the phi I or theta I. Therefore, we have to consider parameters that do not change when the mobile device rotates in any orientation, and it is direction difference of arrival or DDoA. In this figure, we can see that beta ij is the DDoA between the signal from the ith base station and the signal from the jth base station. When we call that the vector demonstrating the 2 signal is di and dj. We have the value of DDoA beta ij is unchanged and independent of the mobile orientation. Now we go to the second section. It is about hybrid DDoA-ToA least square method. We link the estimated azimuth and elevation angle to the DDoA, and in the following computations, the coordinates is considered to be in the reference frame attached to the mobile device. We have, this is the coordinates of the vector di, and this is the coordinates of the vector dj. We have their scalar product. And how, on the other hand, this is the definition of the scalar product. Therefore, we have the equation of true DDoA in terms of the phi I, phi j, theta I, theta j, and this is the estimated DDoA in terms of all the estimated azimuth and elevation angles related. Now we link the coordinates of the base station and mobile device to the DDoA. And in the following computation, the coordinates is in the true Cartesian coordinate system. This is the coordinates of the vector di, and this is the coordinates of vector dj. We have the scalar product, and the definition of scalar product. Therefore, we have this equation, and substitute di by this, dj by this. We have this equation. We can see that it is not straightforward to compute x, y, and z from the coordinates of the base station and the DDoA concern. So we use di. We use the estimated di and dj in estimation. To estimate the distance, we use the time of arrival TOA. We consider the estimated di equal to c multiplied by estimated ti, where c is the speed of light, and the estimated time of arrival equal to the true time of arrival plus an estimation error, where the estimation error is assumed to be zero, mean Gaussian distributed. In matrix formulation, we define this the matrix A, the vector omega, and the vector b hat, where the di hat is estimated by the TOA, and the beta ij hat is the estimated DDoA derived from the related azimuth and elevation angle. In least squares method, we have A multiplied by omega is approximated to b hat, and the estimated of omega is the value that minimizes this value. Therefore, we have omega hat equal to inverse shadow of A multiplied by b hat, where this is the equation of inverse shadow of A. The estimated position of the mobile device is the three first elements of the omega hat. We propose the hybrid DDoA-ToA maximum likelihood estimator. In vector form, we denote this is the vector r hat, and this is the vector f with the variable of x. Now we have the cost function. This is the cost function. Our task is to minimize the cost function, and it is equivalent to find the x that minimize this value. We use Gauss-Newton iterative procedure. At the u+1 iteration, we have this is the equation of Gauss-Newton iterative procedure, and the initial point of the procedure is the result of least square method, and epsilon is the stopping criterion. Now we move to the simulations and results. We define the term least root mean square error to compare the algorithms. This is the equation of the root mean square error. We take the difference of the true position and estimated position. We take the average of all the trials, and then we take the square root. In the simulation, we consider a space or a square of 1000 meter by 1000 meter with the height of 20 meters. And we have the 8 base stations around the area. They form a circle. And at each base station, we have 2 antenna arrays at the height of 10 and 20 meters. An iterative procedure has 3 possible outcomes. There are convergence, divergence, and oscillations. This is the table how we treat the three possible outcomes. If the procedure is converging, we take the final position of the procedure as the estimated position. If it is diverging or oscillating, we will take its initial position. And with considering the standard deviation of all the DOA measurements is the same sigma, and the standard deviation of all the TOA measurements is sigma TOA, and stopping criteria will be 0.01. This is the table. This is the figure that compares the RMSD when the standard deviation of TOA measurements vary from 5 nanosecond to 50 nanosecond. We compare 8 scenarios, 8 algorithm. We can see that when the DOA estimation is small enough, our proposed method is better than pure TOA, and when the standard deviation of DOA measurement is larger, is about 3 degrees, our proposed method is better than pure TOA when the standard deviation of TOA measurement is large enough. And now we conclude our work. In our work, we proposed a self-positioning algorithm based on the DDoA, and the DDoA estimation is based on the estimated DOAs. We link the DDoA with the related coordinates of base station mobile device. The least square method and maximum likelihood estimator based on hybrid DDoA and TOA is also proposed. However, we need a positioning algorithm that does not require the help of TOA, and the algorithm are under investigations. Thank you for your listening, and I'm ready to answer on all of your questions. Thank you.